Good. So our first speaker is Jinwei Zhu from the University of Chicago, who will be talking about string stars in the presence of a spatial cycle. As usual, feel free to ask any question during the talk afterwards or in the discussion session. Jinwei, you have 25 minutes. Please go ahead.
Okay, thank you. Let me share my screen. Oh, is this can you see? Oh yeah, so let
Yep.
me use this slideshow.
Slideshow.
Okay.
Good.
Okay, so hello everyone. Uh, First I want to thank the organizer of String Theory seminar. Oh, I should yeah. And my talk will be based on these two recent papers. Here's the plan of my talk. In the first part, I will introduce the string stars in Euclidean spacetime, Rᵈ cross S1 And in the second part, I will start to add a spatial circle S1z. And in the last part, I will highlight some interesting results. So let me first see a few words about this Rᵈ cross S1 So to study gravity theory is often useful to consider a Euclidean spacetime, which is asymptotically flat with the Euclidean time circle compactified. At infinity, the circumference of this Euclidean time circle is fixed to be some value called beta. And under this boundary condition, the classical solution, which is the saddle point of action, gives rise to the free energy of the canonical ensemble at a temperature equal to this value beta. A famous example is the Schwarzschild black hole in Euclidean signature. So this is the metric, the Schwarzschild metric. But more explicitly, we can look at this figure, which describes the geometry in this metric. So as we can see from this figure, at large R, the circumference of the time circle is fixed to be beta, is held fixed. And as R goes inward, the geometry is non-trivial, especially it is capped off at the horizon radius RH. For the capping off to be smooth, RH and beta should satisfy this condition. And to suppress quantum gravity effects, beta should be much larger than the L Planck. And in weakly coupled string theories, even before we get into the L Planck, there's another scale, which is called string scale, denoted by L string. And at the string scale, string corrections are significant. Take the Schwarzschild black hole again as an example. So as shown in the famous paper by Callum, Myers, and Perry, they calculate the leading order L string corrections to the Schwarzschild black hole. And these corrections are negligible only when beta is much larger than L string. So my talk will focus on temperatures near a string scale critical temperature called Hagedorn temperature. So this Hagedorn temperature is comparable to L string. And for example, in bosonic string theory, this beta Hagedorn is equal to 4 pi L string. And in type 2 string theory, it is equal to 2x squared to pi L string. So let me first give a brief review of this Hagedorn temperature. For a heavy string, which means that mass is much larger than string mass, the entropy follows the Hagedorn behavior as follows. So first, the entropy is linear in mass. Second, the proportion coefficient is exactly the value of the Hagedorn temperature beta h. To see the significance of this beta h, let's look at the partition function. So first, partition function is this integration over m, and for large m, because of this linear behavior in entropy, we can write the integrand as this. So we can see that when beta is equal to beta h, this integration diverges. The partition function diverges, so the canonical ensemble breaks down. So this means that this beta h is indeed a limit in temperature in string theory. And what I want to study is the canonical ensemble near Hagedorn temperature. And actually, in this case, there's an effective field theory that we can study. So first, to introduce this EFT, let's investigate which particles should be included. First, there are massless particles. including gravitons and dilitons. Of course, there's also something like the B field, but let's just take it to be 0. Apart from the massless particles, let's also consider such a string tachyon denoted by chi. By the way, here, by tachyon, I mean that there's no oscillation on the string worldsheet. It does not mean that the speed is larger than the speed of light. So this is string tachyon, what string tachyon means. So let's consider such a string tachyon chi. It is wound around the time circle once. So the mass for this string tachyon is given by this formula. We'll see why there's a subscript infinity here. But now let me note that on the right-hand side in this mass formula, there are 2 terms. The first term is simply the string tension squared times the length of the string squared. And the second term is the 0-point energy on the string worldsheet. So that's why we have this formula for the mass. And let me stress that this mass is actually, this Hamiltonian square is an important parameter that we'll often use later. It measures the difference between the temperature to the Hagedorn temperature. So from this formula, we can see another interpretation of this critical temperature beta h, namely when beta is smaller than beta h, chi, this string winding one string tachyon, really becomes a tachyon because m squared is negative. Furthermore, we can see from this formula that when beta is near beta h, this winding one string tachyon is light because the mass is small. So it should also be included in the EFP. So now we are about to write down an effective action for this EFP. So first, to proceed, first let's rewrite the g tau tau as an exponential of 2 phi. And this field phi is usually called radian because it modifies the radius of the time circle. So when the radian is turned on, the length of the string tachyon becomes, the length squared becomes beta squared times g tau tau. So the mass formula should be modified correspondingly, like this. Since we are considering canonical ensemble, we should fix, as I said, we should fix the circumference of time circle to be beta at infinity. This means that at infinity, phi should go to 0. So in turn, we have this mass reduced to the formula with phi turned off, namely the formula in the previous page denoted by infinity square. So now we understand why there's a subscript infinity here. This simply means that this is the mass of the winding one string tachyon at infinity. I want to consider a small radian, namely phi is much smaller than 1. In this case, we can expand the mass formula as follows. So the first term is just m infinity square without any phi. The second term is linear in phi. These 2 terms could be comparable, so let's keep them. But higher order terms like phi squared, phi cubed, they are subleading to linear term because phi is much smaller than 1. Furthermore, let's also consider the regime where m infinity is small in string units. It also means that beta is close to beta h. Because recall that m infinity square is basically beta squared minus beta h squared. That measures the difference between beta and beta h. So m infinity is small, it means that beta is close to beta h. And in this case, it turns out that the coupling between chi and phi, which is through the mass term for chi, this coupling is dominant over other couplings, such as the coupling between dilaton and chi. So we can neglect the dilaton as well as the other parts of graviton in the effective action. So to write down the effective action, we should reduce on the time circle because we're considering the canonical ensemble. Let's reduce on the time circle and the phi. The resulting effective action is on RD. This is the formula. So the first 2 terms are just kinetic terms for phi and chi. Again, the coupling between phi and chi dominated, so I neglect delta and other parts of the graviton. So now the effective action only includes two fields, which is simple, phi and chi. And these are the kinetic terms. Note that chi is actually a complex field. The reason is that the closed string has orientation. So the string tachyon with winding number -1 corresponds to the complex conjugate of chi. So that's why chi is complex scalar field. These are the kinetic terms, and the last term is the mass term for chi, where I only keep the leading two terms in the mass. And note that this phi chi square is exactly the coupling term between phi and chi. So I want to solve this effective action. I want to consider the simplest case, which is just a spherically symmetric case, which is an analog of Schwarzschild black hole, which is also spherically symmetric. And I also want to consider real chi. And in this situation, I can write down the equations motion as follows, these two equations. And these equations motion possess a scaling symmetry, which allows us to get rid of dimension for parameters like alpha prime and m infinity. So by taking this rescaling, the resulting solution does not depend on the dimension for parameter like m infinity. Okay, so that is the thing we call string star. It's just a classical solution of the equations motion. And in general, there are no analytic solutions to the equations motion, but they can be solved numerically. The boundary conditions we impose is that the derivatives at origin should vanish. Otherwise, there will be conical singularity at origin. And the boundary condition at infinity is that fields should go to 0. Chi should go to 0 because it's bounded. Phi should go to 0 because the semicircle should be fixed at the circumference of beta at infinity, as we mentioned before. So here I show the plot for the solutions of chi and phi. These are the plots for the monotonic solution. And I've already rescaled the fields and variables, so they do not depend on infinity, as I mentioned. And by the way, so this figure is copied from my previous paper with Rᵈ and Kudasov. And even before that, there's a famous paper by Chen, Mandasina, and Witten, which studied this string star solution and investigate its possible transition into the black hole. So in this figure, I only show the solution for d equal to 3 and 4 and 5. And for other values of d, there are actually no solutions of chi hat and phi hat, the rescaled chi, the rescaled phi. But as we'll see, I'm going to explore some cases beyond d equal to 3, 4, and 5. We can also calculate some more dynamic quantities of the string star. So for the canonical ensemble at the temperature beta, we can calculate the free energy by plugging the solution in the action, which gives the on-shell action. We can also calculate the energy or the total mass of the string star by first taking the derivative of the off-shell action and then take it on-shell. Finally, we can use beta m and f to calculate entropy. Since beta is near beta h, we can also expand beta near beta h, and the leading term is beta hm, which is just the Hagedorn behavior I mentioned earlier. The subleading terms are corrections to Hagedorn behavior due to self-gravitation of string star. Before moving on to the second part, let me say a few more words regarding this higher dimensional string star, namely when d is larger or equal to 6. So in my previous paper with Bartos and Kudasov, we showed that when d approaches 6 as a continuous parameter, the quartic corrections to the effective action become important. But the good news is that higher order terms are still negligible. So more explicitly, the quartic corrected equation look like this. So there are two new terms, which are quartic in phi and chi. And these two new terms break the rescaling symmetry I mentioned before. By using the quartic corrected effective action, we found that when D is slightly larger than 6, there are even solutions at Hagedorn temperature. Recall that for D equal to 6, there's a rescaling symmetry which allows us to write chi and phi as M infinity squared times some universal solution independent of M infinity. So when we take M infinity to be 0, the solutions vanish. So there are no solution at Hagedorn temperature. That's the situation for D smaller than 6. However, when D is slightly larger than 6, the situation is completely different. There's an even solution at beta Hagedorn. That's quite interesting. And we also expect it to be true for any D larger than 6. However, when D is strictly larger than 6, higher order corrections are not negligible. So we're not 100% sure. And by the way, you can see a recent paper by Rᵈ and Wu for discussion on higher dimensional string star. So let's move on to the second part where I turn on this spatial circle. The circumference of the spatial circle is called L, and I will assume that L is much larger than L string, so that string corrections associated to this Z circle can be suppressed. So the motivation of turning on this S1Z comes from the black hole case, where the structured black hole is uplifted to a uniform black string. Explicitly in terms of the metric, there's just an additional dz square. So this Z is basically like a spectator. There's nothing to the whole solution. So that's why the solution is uniform along the Z circle. However, there also exists black string solution which is non-uniform along Z circle, or even black hole localized within the Z circle. They exist in the range for beta smaller than some value, which is of the same scale as L. What's interesting is that when beta decreases, the uniform black string transitions into the non-uniform black string at a critical point. And this critical point is equal to L up to some numerical factor. And this transition is the famous Gregory-Laflamme instability. And as I mentioned, this GR is only valid when beta is much larger than L string. And what I want to investigate is if there's any analog of Gregory-Laflamme instability when beta is of string scale, in particular when beta is near the beta Hagedorn. So to investigate beta near beta Hagedorn, we come back to this Horowitz-Polchinski effective field theory, just the effective field theory I was talking about previously. So what's new to the effective action is just that there's a Z-dependent term. There's an integration of a Z, and and by the way, for the kinetic term, there's also a derivative with respect to Z. So now, if we look at the uniform solution, of course, we can integrate Z out, and the uniform solution does not care about the parameter L. But for non-uniform solution, there's a new dimensionless parameter, M infinity times L. So L has the unit of length, and M infinity has a unit of length inverse length. So together, it is a dimensionless parameter. So even after rescaling, non-uniform solution could depend on this new dimensionless parameter. So let me show an example for D equal to 4. Here are the contour plots for the field chi, and in each figure, the horizontal axis is R from 0 to some finite value, and the vertical axis is Z from 0 to half period. So there's another half period down here, which is the Z2 reflection of the figure shown here. So as we start from a relatively large value of M infinity L, and as we can see, for this value of M infinity L, the solution is localized within the Z circle. As we gradually decrease M infinity L, the solution becomes more and more uniform, and at a critical point, it becomes completely uniform along this Z circle. And by the way, when I've published my first paper, there's another paper by Amperon and his collaborator, which also studied non-uniform string star solution. And actually, my first paper is some perturbative analysis. And in the paper by Amperon and his collaborators, they developed some non-perturbative techniques, which I utilize in my second paper, for example, to generalize these figures. And note that I also want to note that the critical point for the non-uniform solution to become uniform is that M infinity equal to 1 over L up to some numerical factor like 4.8 for d equal to 4. Note that previously I mentioned that M infinity should be small in string unit. That's the regime of validity. Because I'm assuming that L is much larger than L string, so this critical M infinity is still within the regime of validity. It is still small compared to the string length or string mass. So finally, let me highlight some interesting results. I only talk about the interesting results in my paper and skip the result which is less interesting. But if you want to look at a more complete result, you can look at my figure. Let me highlight the interesting one. So the interesting things happening in D equal to 3 and 4 is that when I compare the entropies of uniform and non-uniform phases at the same mass, I found something interesting, namely, first, the uniform solution should undergo the first order phase transition at a critical mass. However, the non-uniform, if I look at the whole non-uniform branch, it always has a lower entropy than the uniform branch. So the uniform string star cannot transition into the non-uniform string star. Then the puzzle is that which phase can the uniform string star transition into? The answer is that there also exists a non-uniform black string around this critical mass, and it can be checked that this black string has a much larger entropy. So it's reasonable to propose that the uniform string star can transition into the non-uniform black string at a critical mass. And this builds a direct connection between string star and the black hole. So previously I said there's no solution at d equal to 2. The problem is that phi diverges logarithmically, so it does not go to 0 at infinity. However, there still exists boundary solution for chi. Here is an example. And what's interesting is that when I vary infinity L, I found that non-uniform solutions never become uniform. To see that, I noticed that the difference between the field at z equal to 0 and z equal to L over 2 never becomes 0 when I vary infinity L. Here is the details. However, that does not mean that uniform solutions don't exist. They do exist. This is an example, and any other uniform solution can be generated from this example by a scaling transformation. And the scaling symmetry means that all the uniform solutions are equal. No one is special for the non-uniform solution to transition into. And this is the understanding of why there's no transition from non-uniform solution to uniform solution for d equal to 2. So for d equal to 5,
Jinwei,
interesting transitions.
just
Sorry?
let you know that you have 2 minutes left.
Okay, I will certainly go through it in 2 minutes. Okay, so for d equal to 5, interesting transition scenario happens in the canonical ensemble. So if we don't consider quartic corrections to the effective action, as was done in the paper by Amperon and his collaborator, what we would find is that the non-uniform solution always has the larger free energy than the uniform one. Then there will be a puzzle, namely, there's a similar puzzle as in the d equal to 3 and 4 case, namely there's no phase for the uniform solution to transition into. Well, to resolve this puzzle, we just simply take the quartic corrections into account. And what I found is that when the non-uniformity increases, the quartic corrections become more and more significant, and that dramatically changes the phase diagram. Let's look at the phase diagram more explicitly. So here, the horizontal axis infinity, and vertical axis is the free energy up to some factor. So by tilde, I mean that I strip off some factor like 1 over g Newton or something. So as we can see, there exists a critical point where the uniform branch is connected to the non-uniform branch. And around this critical point, the non-uniform branch has a larger free energy than the uniform branch. So below this critical point, the uniform solution is stable, and above that, above this is unstable. For the non-uniform branch, as the non-uniformity increases, it first goes in this direction, but finally it goes to another direction. And when the non-uniform solution becomes more and more localized, it has a lower free energy than the uniform solution. So now we understand that at this critical point, the uniform solution can undergo the first order phase transition and jumps to the non-uniform phase. For d equal to 6, I also compared the entropies of the uniform non-uniform phases at the same mass, and I found something anomalous. So by comparing entropy at the same mass, it's like a microcanonical ensemble, and that's basically saying something for Lorentzian signature. So if this result is indeed continue to the Lorentzian signature, what I found is that the uniform solution is stable when spatial circle is larger than the critical size. That is the opposite of gravity-Laflamme instability. So for gravity-Laflamme instability, if we trust classical dynamics, we would expect that when the spatial circle is large, the KK modes are more likely to develop instability. But here, it seems that the situation is the opposite. Well, maybe we just cannot naively continue the results to Lorentz signature because the winding one string tachyon does not have a Lorentzian interpretation. So because in the Lorentzian time is not compactified, right? So there's no analog of the tachyon wound around the time circle. Well, so that is all the things I wanted to talk about. Thanks for listening.
All right. Let's thank Jinwei for his nice talk. Are there any questions?
Hi, Jinwei. I have a question. Yeah. So my question is also motivated when you showed the D equals 2 case, but also more in general. Is there like an easy generalization for like multi-centered string stars? Should you expect things to behave normal, or would you expect some interesting behavior?
Oh, that's an interesting question. Oh, so for the black hole case, I think there's an analog, and even there's a paper whose title is like a multi-centered black hole in D equal to 2, and I think there should be some analog of that, but I didn't investigate that. But I think it's interesting to investigate more. Thanks for the interesting question.
Yeah, I was thinking D equals 2 because since like things like do not go to 0, but like blow logarithmically, maybe yeah, there was something there. But I'll check.
Yeah,
I'll check the literature.
diverges.
Yeah.
Yeah.
Okay. Thanks.
Okay. So since we're running out of time, and if people have other questions, you can stay in the